So we'll start from n, then choose the local coordinate system in which gamma prime is 0, move it a little bit to the neighbor. Okay. Then change coordinate system so that gamma prime is 0 at the neighboring point. Okay. Move it a little bit and go this way from here to here. Okay. So that is the notion of parallel transport along a curve. Exactly. At each point, you have to make that choice, right? So you move from n prime, right? You take a neighboring point where it's n prime. Now you change coordinate, right? So n prime will change. That vector you parallelly transport to the neighboring point. Right? Then again you change coordinates, so n prime will change because you have seen that n tangent vector changes under a change of coordinates, right? So that's the procedure. Yes. Exactly. Yeah. So you guys think of the sequence of line elements, small elements, right? And you do this infinitesimally, and then you take the limit when the length of each line element goes to 0. Yes.
So we are defining a mapping from a tangent space to other tangent space.
Yes, exactly.
And it doesn't matter which vector we choose initially, which vector.
Yeah, any vector you can choose, and the final vector will be the parallel transport of that vector. Why are you doing? Because you want to know the notion of parallel. Okay, I mean we are trying to distinguish what happens in flat space versus curved space, right? So you try to make the curved space look as much as flat space as you like. I'm trying to repeat all the properties of the flat space, and then see where it breaks, right? Because that is the intrinsic difference between the flat space and curved space, right? That's what we are trying to do, right? Now the parallel transport, you can say in flat space, right? We know what parallel transport means, but suppose you are given polar coordinate system in flat space, right? Then in polar coordinate system, a parallel transport of a fixed vector, right, is not just the same vector moved to another point, right? So even in flat space, in a defined coordinate system, you have to define the notion of parallel transport this way, right? And that should coincide with the usual notion of parallel transport in the Cartesian coordinate system, right? In flat space, the analog of the prime coordinate system is the Cartesian coordinates, and that is valid everywhere. Right? Once you choose the Cartesian coordinate, that same coordinate gamma vanishes, and so the parallel transport is just take the vector and move it. Okay, you are trying to generalize that notion in curved space so that we can eventually distinguish between properties of flat space and the properties of curved space.
So this in prime vector, these are not the abstract tangent vectors that on the space, right? These are in the coordinate space, right? These are elements of Rn.
Yes, so the tangent space also is Rn, right? I mean, we introduce the n, right, by saying that for every n there is a geodesic. It's a space of geodesics passing through a point. At this stage, you are not worried about the geodesics, right? We are just thinking of this as a vector in Rn which you want to move, right? Yeah. So forget about the fact that n corresponds to geodesics, right? Now we are just thinking of that at every point there is a Rn, right? These are different vector spaces, right? They may be equivalent, but there will be different vector spaces because tangent spaces are different. Right? And you want to find a map between one tangent space to another tangent space, right? And that's the way I'm defining the map, right? Giving any vector in the first tangent space, I want to find the corresponding vector in the second tangent space. So you could change your vector n prime, right? And this will be different. Right? So this procedure tells us that given any vector n in the first tangent space, how to find a new vector m in the tangent space here. This is giving a map between one tangent space to another tangent space, right? So tangent space are x0 and tangent space is x0 plus delta x0. Given a vector in the tangent space of x0, we have to give a rule of what is a vector in x0 plus delta x0. I am saying that take the vector n prime, right, which is defined as a n component object. right? And take the same n component object, n x naught plus x delta x naught. Yeah, that's true, but eventually that really doesn't really make a difference, right? In the limit when you take the size to 0, right? It can be either from the point you are moving from or to the point you are moving to.
Are we assuming that when we move from x naught plus delta x, the coordinate transformation for which the Christopher symbol is 0?
No, no.
So we'll have to
change coordinates, exactly, right? So once you have moved to delta x naught, say you make a convention that you will always take the starting point and make the Christopher symbol 0 at the starting point. Right? Let's take this in uniform convention. So you start with x naught, right? Then you move to x naught plus delta x naught by in that coordinate system in which Christopher symbol is 0 at x naught. Then at x naught plus delta x naught, you have to now change your coordinate system, right? Because their Christopher symbol is not 0. So n will change, right? That new vector, parallelly transport to the neighboring point. Okay? And then again, you change coordinates. You get a new vector, the same vector, but it's in a different coordinate system. So the components are different. That you shift to the next point and so on.
Parallel transport mapping tangent space the coordinate system where gamma is 0.
But once you have defined the map between two Hilbert spaces, right? You can now make a coordinate change, right? You can go back to the original coordinate system.
But while defining it, we are using this coordinate.
Exactly.
But in principle, we can kind of have the different.
Yeah. So let's suppose that you have some coordinate system x in which you want to finally express everything, right? Once you know the what the vectors are at different points on this curve, all of these can be transported back to x, right? Because at every point, x and corresponding x prime has some relation. Right? So using that relation, you can always go back to the x coordinate system. So ultimately, the picture is that in the x coordinate system, right? If you want to represent this, the vector will actually change, right? The components will not remain the same. Okay? It's only in the x prime coordinate system that it looks like at every infinitesimal step, the components remain the same. Yes, yes. So you are assuming that we have invertible coordinate transformation. Okay, so non-singular invertible coordinate transformation. Yes. That will be a different parallel transport. May be different. We'll see. We'll see if it's different or not. Yeah, that's one of the questions we'll try to address. Right? But first, you should first understand what parallel transport means. Yes. So as at different points, right, you will find different mappings. Any? You can define it for any PQ tensor, but right now, the way you have defined, let's do it for vectors, right? Yeah, eventually we can do it for any PQ tensors. Okay? But that may be confusing because the point is that if PQ tensors are already defined at all points to begin with, right? That's the way you introduce tensor fields. Okay? If you start from here, right, define and parallelly transport it to a neighboring point, that may not agree with the predefined tensor field at that point. Right? Just like a vector field, right? Imagine I have a vector field, which is defined everywhere in space. Now you can say that, okay, let's just pick one particular point, right? Take the value of the vector field and parallelly transport it. Regard this as a tangent vector like this and parallelly transport it by this rule. Okay? It will give you some set of vector fields along this line. But those may have nothing to do with the vector field that we had started with. But vector fields are not supposed to, their derivatives are not supposed to vanish when the Christoffel symbol is 0. I have not said anywhere that the derivative of the vector field vanishes to the Christoffel symbol. Then the covariant derivative will be 0, right? Right? Yeah, but we are not demanding that a vector field has covariant derivative 0. A general vector field need not have covariant derivative 0, right? So if the vector field had covariant derivative 0, then this is true. Right? Because then in the coordinate system, the Christoffel symbol is 0, right? The ordinary derivative vanishes. Okay, and that means the vector field will not change. Yes. Exactly. It will not be r hat. Exactly. Yes. Exactly. Exactly. That's exactly the point. Exactly. That will change the components. Right? Then you move it to a neighboring point. So the change in components actually is happening because you have to keep making coordinate transformation, right? Exactly. Yeah, we'll see that you have to keep up to certain order, right? It's a question of what order you want to keep it in, right? So that you have to make sure that as you take the interval to 0, right? You have to make many more steps, right? And you have to make sure that those steps don't accumulate to give you something finite. Okay, now this is the correct definition of parallel transport, okay? But this is not very practical, right? You can't just take a line divided into infinite number of points and keep making coordinate transformations, right? So what we need to do is to find a definition of parallel transport without changing coordinate system, right? Suppose you have fixed x coordinate system. Okay? In that coordinate system, right, we know that the vectors should change as you move along the curve, right? The components should change because you are making these coordinate transformations, right, at every stage. So then what is the way the same parallel vector itself has the same component in the prime coordinate system. That's why I'm using n prime I. So that's the form of ni at x naught plus z. We have gone back, we have pulled back from prime to unprimed coordinates. Is this clear? Now, exactly. So that's why I'm using use the same n prime, right? Otherwise, I have to change these two also to n prime at x naught plus delta x naught, right? We have used the same n prime, right? That's why the fact that it's a parallel transport is going in. Is this clear? And now let me also say a few words about why we can ignore these higher order terms. Right? There are also delta x naught squared term, right? Why have we ignored it? The reason that I have ignored it is the following: that ultimately this has to be done in many steps, right? That's what you want to do, right? You have to do say steps of length epsilon, and you have to do order 1 over epsilon steps, right? If each step has length epsilon, you have to do order 1 over epsilon steps. So any order epsilon term can actually lead to order 1 term because you are multiplying it by 1 over epsilon, right? You do it 1 over epsilon term times, right? So order epsilon terms you cannot ignore. Okay, because order epsilon term you have to keep repeating 1 over epsilon times. For order epsilon squared terms, right? If you repeat it 1 over epsilon times, you are still left with an epsilon. So that's why you can ignore the order 1 over order epsilon squared terms. Yes. So order epsilon term, right? So ultimately, so this is a step epsilon, right? So you have to do it 1 over epsilon times to remove order 1 distance. Okay. So if every step gives a contribution of order epsilon, it can build into a finite value because there are 1 over epsilon steps. Now, by ignoring these terms, you are making an error of order epsilon square at every step. Right? But those can at most build to order epsilon, right? And in the epsilon goes to 0 limit, we can ignore. Okay? So that's the reason why you can ignore these higher order terms. But this one we cannot ignore. Is this clear? So this tells us that ni at x naught plus delta x naught is given by ni at x naught plus this quantity or also at x naught. Well, this is n prime j at x naught. Yes. Well, n prime j by definition was what it was at x naught, right? But now I'm going to rewrite this in the unprimed coordinate system because you have to write everything in the unprimed coordinate system. So delta x prime k is right? Because it's just chain rule, right? Change in x prime is given by the derivative times delta x. And this one we had found last time, yesterday, the transformation law, right? So if you want to convert this to the unprimed coordinate system, it's clear? So now the point is this quantity is a little inconvenient, right? Because he still knows about, tells us that you have to first find a prime coordinate system, right? And that is exactly what you want to avoid, right? You don't want to explicitly find the prime coordinate system at every point. Okay, that beats the purpose. So you have to somehow express this in terms of something that you know, okay, which doesn't explicitly refer to prime coordinate system. Is that clear? Again, whether it's at x naught or x naught, okay. Normally, the way when you write this, the x naught means here it's at the x naught coordinate, x coordinate system x naught, right? That's the same as x prime coordinate system x prime naught. Right? The reason that I have written it x naught is because normally the argument that you write is the one with respect to which you differentiate. Right? So that's why if it was x up and x prime below, I would have written x prime naught. Right? That's the usual convention one uses, right? When you write, say, del y del x, right? We write the value at x naught. Yes, this should be x naught prime. Thank you. Yeah, these are all x naught prime. Thank you. Okay, but of course, x naught prime is the image of x naught. Okay, so it's same. So what we are going to do now is to use the coordinate transformation law of the Christoffel symbol. The relation between gamma prime and gamma, okay, which you had written down earlier. I am going to write it again. So gamma prime ijk This was the general transformation law of gamma prime, gamma that we had written down. Christoffel symbol, right? So this part is a tensor transformation, would have been just tensor transformation. This is the extra piece, right, which makes it not a tensor. Is that clear? Now we are going to put x prime equal to x prime naught, okay, which is the same as x equal to x naught. So if you put x equal to x naught or x prime equal to x naught, x prime naught, then the left hand side is 0 by construction. Because x prime is a coordinate system in which gamma is 0, right? Gamma prime is 0. So add x prime equal to x prime naught. Gamma prime I j k x naught prime is 0. This means this is equal to These are all evaluated at minus. Thank you. Pardon? This one? Second term. Okay, del x. Okay. Yeah. Thank you. So the idea is that you are not going to use this equation to extract this and put it back there. Because you have something like this, right? Oh, yeah, we have that quantity is what we want to extract. Is that clear? Yeah, yeah. So the x naught prime, I'm just not writing it. Okay. It should be understood that everything is evaluated at the point x naught, right? Or x naught prime, depending on what coordinate system you use. Yes. Yes.
By that expression, and then by sort of using a reverse chain rule, LX prime case, K index will be contracted, right?
Yes, indeed.
And then that would remove the derivative.
But that will basically give you ddx of this,
yeah,
right? Which is not very useful. Okay, you can write it that way. You are right that it is ddx of dx prime, right? But normally you want to have the derivative respect to the same thing, same setup, same variables, right?
But then you could use the other term as well to remove the K derivative, and then you would.
Oh, that is inside. You see, that is inside, right? So you have okay, but this has gone inside the derivative, right? So if you try to bring this in, this will have to act on that, right? So it will give you back a similar term. So that is the reason, I mean, you cannot, this is not a tensor. Otherwise, if you could remove the second derivatives, right, then this would be like a tensor transformation, okay, which is, it is not. But this now tells us that, gives us something, because let's see that combination that we see here, right? Well, this combination is still not what we see here. Okay. So we can basically, let me change this to L. Okay, I just change R to L in this, so that this part is common. Okay. So basically, we can remove this. Same matrix multiplying both. Okay. This is, as long as this is invertible, right, you can just get rid of this. Right. If you want to do it formally, okay, we can do it, which is that multiply it by something like this. M is not there, so this multiply this by this and sum over R. Right. So there will be a Kronecker delta ML, right, on this side. Similarly, there will be Kronecker delta ML on this side. Okay, so that will give the equation with L replaced by M. Okay, so this is something you have to get familiar with, right? Every time you, instead of multiplying, right, the same matrix is contracted, so you can just remove it, right? Because this is invertible matrix. Is this clear? Okay, so what I'm claiming is that given this, we can simply cross this out. Okay, but if you want to see more formally, you multiply by this matrix that I just wrote, right? The derivative of xm with xl with respect to x prime m. Sorry, xm with respect to x prime I, contract I, right? You get a Kronecker delta, and then that removes this in matrix. Okay, so you have almost gotten there. So let's look at this. So this term now can be written as minus. So this combination is what we got is, okay, let's look at the index. This is ijk. Where are they? What are the indexes? Ljk. So you have to change L to I on this side. Okay, so this came from here, and then we multiply it by okay, everything is at x naught or x naught prime. Okay, I'm not writing them explicitly. Is this clear? So this part, so this, let me use the yellow chalk. So this part over here became this. I still have to write those other factors. That's it was right in x naught L, right? This is changed from x naught to x naught plus delta x naught. Is this clear? So now you can actually simplify it further, because you see that by chain rule, this combination, right, it is difference with respect to x prime, and then again it difference with x prime with respect to xm. So this is the canonical delta of Sm. So that sets S equal to M. Similarly, this combination is canonical delta of TL. Okay, so I can just set T equal to L. So this becomes minus gamma I. So S becomes, what did S become? S became M, and T became L, ML. So after all these steps, you have gotten rid of the prime coordinate. Right? Because this is expressed purely in terms of the quantities in the original coordinate system. So let me write again here. So what we prove by this is equal to minus gamma I ML okay, so this was x naught. This one was x naught plus delta x naught. And this one is telling us how much n changes under parallel transport. So now you see in the x coordinate system, the components of n are not fixed. Components of n are actually changing. In the x prime coordinate system, the components of n are fixed. In the x coordinate system, they are changing because the transformation from n to n prime at this point is different from the transformation from n to n prime at this point. Okay, so the change happened because of that transformation. Right? Even though the vector in the prime coordinate system, the vector components are identical. Is this clear? So now we are going to make this into a differential equation. Okay. So let's suppose that u parameterized. Suppose u is the parameter along the curve. Okay, C is not necessarily geodesic. C is any curve. Right? Parallel transport can be defined along any curve, not necessarily geodesic. So suppose n u is a parameter along C, okay? Then this tells this can be written as dxi dni du. Right? You are making a small change in u, okay, is minus gamma I ml So we derive this at x naught, but of course it's true at every point. Right? You can start from x naught plus delta x naught and do this. Okay? And because now we have expressed everything in the original x coordinate system, right? We can write a single differential equation because you don't have to change coordinates anymore. Right? In the x coordinate system, this is a differential equation. So this is a parallel transport equation, right? This we can also write as by taking everything on one side.
We now take initial NI and
Exactly.
parallel transport it. So we'll say that these two geodesics are parallel.
These two tangent vectors are parallel. Exactly. Tangent vectors, yes. This one? So what did I miss? Okay, so this corresponds to u plus du, right? And this corresponds to u. Yeah, so I have written the argument because earlier I hadn't introduced the u parameter, right? But at u, the x is x naught. At u plus delta u, x is this. So this is a change between as you go from u to u plus delta u, right? So because otherwise I have to write dni dx naught and then dx naught du, right? I mean, what you are suggesting, I could have written it as this. But this is somewhat inconvenient because this tells us that to calculate this, right, you have to know how to parallel transport n along all directions, right? To define this, you have to know under arbitrary change in x, how n changes. We of course know, but what you want to know is only along the curve. That's why we write this directly as d and du. Yes, you could get n square PDEs, except that they may not have a solution. See that if those n square PDEs will have a solution if parallel transport along all curves give the same result, right? That is not guaranteed. That's the question we was raised once, right? That if you take two different curves, right, and parallel transport, they may not agree. Right? So you can write n square PDEs, right, but they may have no solution. This one we are sure has a solution, right? Unless you run into singularities or something, if the metric is smooth, right? This is a single differential equation, right? So you are giving an ordinary differential equation. So once you are given n initial conditions in the form of the vector component ni at x naught, you just evolve by this differential equation to get ni at any other point along the curve. Is this clear? Okay. So what Priyanshu was suggesting is that you can define parallel transport in all directions, and instead of writing a differential equation in U, you can write a differential equation like this. Okay. The problem with that is that that differential equation may have no solution, because going in between two neighbors, right? If you go like this, if they give different result, right, then it's clear the differential equation cannot have a solution. That's why you define parallel transport along a curve, not in the whole space. Exactly. Yeah, then the point is you shouldn't write the differential equation in every direction, right? Because when you're writing a differential equation in every direction, the solution will require that there's a single valued function, right? If that doesn't exist, right, if the parallel transport on different curves give different answer, right, then those differential equations will be inconsistent, right? Whereas this differential equation is perfectly consistent because you can write solutions.
If we chose another curve, the solution of that equation may not be consistent.
Exactly. But you are not demanding that that's the case, right? Because you are defining parallel transport such that it's along a curve. Okay, as long as that is kept in mind, right, there is no inconsistency. No, Ni is any vector. Exactly. Ni is any vector, but that you can parallelly transport along any curve. Exactly. Vector that you want to parallel transport will go as an initial condition to this equation. Is that clear? Okay, so now I'll give some exercise. So first is to check okay, this better be true because we did x was nothing special, right? We derived it in x coordinate system, but we didn't say anything about what the x coordinate system was, right? So it better be that if you take that equation, this equation, and make a change of coordinates, right? We know how Ni transforms, right? You can keep the same because it's a intrinsic parameter of the curve. You know how Ni transforms, you know how gamma I transforms, right? Put all those things together, and you can check that the equation preserves its form. Right? If that equation holds, then it will also hold with everything replaced by prime. Okay, then replaced by n prime and gamma replaced by gamma prime, and then dx prime du. The second, again, is obvious from what we have done, but this is something you can again check in a general coordinate system. Okay, the norm of this vector n, okay, using this metric G, doesn't change. This is obvious in the coordinate system in which gamma is 0. Because in that coordinate system, derivative of G vanishes, first derivative, right? Because G doesn't change. And n was defined so that the n doesn't change in that coordinate system, right? N prime was just component by component equal at neighboring points, right? So in that coordinate system, this is obviously true. So it better be true in a general coordinate system, right? Because this is general coordinate invariant. Okay, but this you can check explicitly. Just calculate this, right? For d and du, you substitute that from there, and you can check that this is true. Okay, now let me make some observation, okay, which is that the parallel transport rules are linear. So what do you know? They are linear. Okay. This means that if N1 of u and N2 of u are solutions, then An1 of u plus Bn2 of u is also a solution. Okay, just because the differential equation is linear in N. Right? You can just see from there. If N1 is a solution and N2 is a solution, then take any linear combination that will obviously satisfy the differential equation. So this means that suppose we start with a vector n, N1, and it is transported to M1 along that curve C. You start with another vector N2, it's transported to M2 along that curve C. So now if you start with AN1 plus BN2, it will get transported to AM1 plus BM2. Right? So if N1 is transported to M1 and N2 is transported to M2, then AN1 plus BN2 is transported to AM1 plus BM2. Is this clear?
This seems to be the same statement.
Yes, same statement. This is about the differential equation. Right? This is about the initial and the final values. This means that we can write the relation between M and N as a matrix relation. So we can write M, okay, which is this is a transported vector. Let me. Yes, the coefficients are exactly same. Which coefficients are A and B, you mean? Yes, indeed. Because they are the same because the rules are linear, right? Okay, if you start with N1 and which transports to M1 and N2 that transports to M2, then AN1 plus BN2 will be transported to this because that's as a consequence of this, right? See, this is a solution. So this at u equal to 0 is AN1 plus BN2, and this at u equal to 1 is AM1 plus BN. Okay, so this shows that if you start with AN1 plus BN2, you reach AM1 plus BM2. So this means that M can be written as a matrix which depends only on A, B, and the curve C on N. This is a matrix. N by N matrix. A is the initial point, here I have drawn. A is the initial point, B is the final point, and C is the curve. So the matrix depends on the initial and the final points and the curve that it follows. Is this clear? As long as the metric is non-singular, it's non-singular, right? It can be singular if the differential equation has problem. Right? As long as the differential equation is non-singular, because you see that it preserves the norm, right? So if Gij is non-singular, right, then the matrix is non-singular. Now, what else can you say about this matrix? So let me say something first. That M, so let me call M B A minus C. Okay, what this object is. So you see, B A means the B is now the initial point, A is the final point, and minus C means that you are traversing C in the opposite direction. Okay, so that's the notation. Minus C means that C traversed in opposite direction. So here, let me draw an arrow. Yeah. So the arrow is reversed. Any guess what this is? It should be M inverse. Is it obvious that it should be M inverse? Linearity has to play a role, yes. Pardon? Yeah, but it's not always true, or not all differential equations, or not all differential equations have this property. Pardon? It's a linear differential equation. Yes, that told us that you can write in the matrix form. Coordinate transformation is invertible. Yeah, that's not a problem, right? But as a differential equation, right, it requires some other property. Yeah, so U2 minus U symmetry is needed. Imagine Newton's equation with friction, right? That's not reversible. If you start a particle, right, it with some velocity it reaches there, right? And then you start from there with an opposite velocity, it doesn't quite come back to the original point, right? Because friction is not invertible under t goes to minus t, right? So that's important. This equation has u goes to minus u symmetry, right? Or u goes to 1 minus u symmetry, right? So that u ranges from 0 to 1, that by that symmetry u goes to 1 minus u, right? The initial point can be mapped to the final point, and final point can be mapped to the initial point, right? So that's part of the input why this is true. No, U transition symmetry will just translate the curve. We have to reverse, right, the direction. To prove this, right, we have to reverse the direction. So we start from N1, right? We evolve and we go to M2, M1. So we start from N, we go to M, right? Now we are saying that let's start from M, right? Follow the same differential equation, but along the reverse curve. Will it reach N? Right? And what I'm saying is that in mechanics, it doesn't always happen, right? You start from A, give it a push, it reaches B with some velocity. You start from B, give it a reverse velocity. Will it reach A? It will reach A if the dynamics is reversible. But suppose there is a friction term in the equation. That will not happen, right? Start from A, you push it and it reaches B at, say, small velocity. If you just reverse that, it's not going to reach A. So absence of friction, right, which formally is the statement that the equations are invariant under u goes to minus u, that's important. Okay, with that, this is true. From this, yeah, so from this equation, basically the point is, suppose n of u is a solution. And n of 0 is n, and n of 1 is n. Suppose, right? Suppose you have a solution like this. Okay. Then the statement claim is that n of 1 minus u is also a solution. Okay. This you can see by substituting that. Okay. Just take the function, replace u by 1 minus u, right? And change, you can change variable from 1 minus u to v, right? And because of the reversibility, in terms of V, it's the same equation. Okay. So n of 1 minus u is a solution. So for this at u equal to 0, the initial point is m. The n of 1 is m, right? And at u equal to 1, the solution is n, right? So you start from m and you go to n. Reverse parameterization. So because of this reversibility, right, by this new parameterization, you can reinterpret the original solution as another solution where you start from m and reach n by traversing the curve in the opposite direction. Okay, now we come to the question that we want to answer. Okay, and that's what distinguishes between flat and curved space. So let's suppose, okay, there are two questions which will turn out to be related. Let's suppose that we have point A and point B, and we have two curves, C1 and C2. So we can write two matrices. Okay, you go along the first curve, you get some matrix, okay, which converts n to m. You go along the second curve, you get some other matrix which converts n to m. Are these the same? Not necessarily. Why? Yeah, well, it could depend on C, of course. True, but after you integrate, this is true also in polar coordinate in flat space, right? Yes, indeed, it does. So which means that it's not necessarily the same. But can it be the same? In flat space, it better be the same, right? Even though if you use polar coordinates, all the objections that you are raising are valid there, right? So it's true that it's not necessary. You cannot say from based on what you have said if these two are equal or not. Okay? That doesn't mean that they are not equal. Okay? You have to understand when they are equal and when they are not equal. Okay? So it only says there is a possibility that they are not equal. But given that in flat space they are supposed to be equal, right, may make us suspect that maybe they are always equal. Right? So you have to try to understand whether that's true or not. The second question, which will be related to this, is consider a closed curve that starts and ends at the same point, A and C. So is M A C equal to the identity matrix? Okay, you start from A, some vector n, go along the closed curve, and come back to A. Yeah, both the questions are equivalent. So let's try to see formally that they are equivalent. that suppose one is true for all cards and all points AB. Then to prove 2, we can do the following. So we have A and this is C. Okay. We just pick some arbitrary point B, some arbitrary point. Okay. So then we can write M A C as M. So first you apply M A B C, right, on this vector, and then you come back M B A. Let's call this C1 and C2. So C is C1 and C2. C is basically C1 plus C2. Sorry, this is ABC1 and this is C2. Here you take a vector, first multiply by MABC1 so that it gets transported to B, and then you multiply it by MBAC2 so that it gets transported back to A. Right? B is just some arbitrary point that I have written. Okay. After all, the parallel transport along this can be thought of as a composition of parallel transport along this and then along this. But this one I can write MAB minus C2. MABC1 minus inverse. MBAC2 is MAB minus C2 inverse, right? By that relation that you had somewhere, maybe I have erased it by now. But you see, M minus C2 and C1 are just two curves that connect A and B. So by 1, if this is true, if 1 is true, then MAB minus C2 is the same as MABC1. So if 1 is true, then MAB minus C2 is MABC1. Right? That's what one says, that the parallel transport doesn't depend on the curve that you get, right? So whether you go along C1 or minus C2, you should get the same result. Okay. So if you use this, then this is identity. Okay. And the reverse is also easily provable, right? You can just leave the, so exercise proves the reverse. Okay, given any 2 points, 2 curves, right, you just make a closed curve out of it, right? That has identity M, okay, and that relates the matrices along those 2 curves. Pardon? That's okay. It doesn't matter, but we have not demanded that it's only for smooth curves. Okay, any curve is fine. Okay, the last thing I want to do now before I make state the results, which I'll prove next time, is the following, that we introduce this parallel transfer along a closed curve, right? M, this is A, and this is C. Okay, so you have this notion of M, A, C. Okay. Suppose you pick another point on this curve, B. And I want to calculate M, B, C. Okay. Are these the same? Yeah, in general, yeah. So nothing commutes, of course. M is an n by n matrix. Right. So what do you think? M, A, B, A, C, and M, B, C will be the same? Same or not the same? It should be same.
In general, for general matrices, it's not true.
Not for general, for this particular matrix. Pardon? 2 points are on the same curve, yeah.
I mean, B or A doesn't make any difference, right? A, if a curve starting from B and A.
Yes, but that is not the same as the curve starting from A and ending at A. MBA is the reverse of MAB. If you have to also specify what the curve is. Okay, yeah, that I'm not saying that they commute. Okay, okay, so let's try to do this. I mean, how to analyze this, right? So what you can do is the following: okay? That you want to move the point to A, right? If you want to express in terms of M, A, C, right? We want to move from B to A. Okay? So we take this curve C1, okay, which is this part B to A. So we write M. So when you want to parallel transport a vector from B to B, okay, what you do is that you first transport it to A. Okay. So M, B, A, C, C1. Okay, that's not what you wanted to do, right? You want to transport it like this, but let's do it, transport it away. Okay. Then we transport it all the way round. Okay, so this part will cancel off, right? Because we transported it and transported it back. And because of the reversibility of the parallel transport, this part will have no effect. Okay, but let's do it. So we'll first transport it to A, then transport it back. So then you get M, A, C. But we want to end at B, not at A. Right? So now you have to transport it from A to B. So you have M, A, B minus C1. Is this clear? Right? So transporting it from B to B, okay, I'm thinking of it as a composition of 3 transformations. One, first go from B to A, then go A all the way to A round, and then from A to B. Right? If you just think of it, that's the same path that you wanted to follow, right? Except we just added and subtracted some extra piece, right? But one after the other, so they just cancel out. Parallel transport is reversible. So this I can write. This is M, B, A, C1 inverse. M, A, C, M, B, A, C1. So it's not quite the same, but it's a similarity transformation of the original matrix. If this was identity, then this will be identity, right? If along some loop, parallel transform matrix is identity, then you are guaranteed that irrespective of where you start, the matrix will be identity. But if it's not identity, right, then in general, it will get transformed by similarity transformation. Some matrix inverse times this matrix times the matrix. Okay, this will be useful in what we'll do later. Is this clear? Okay. So now let me state a result that we will prove next time. Okay, because it's a long proof. That let's imagine that you have some closed curve C. And you want to know if parallel transport along this gives you identity. Right? That's our question 2. Okay? Whether parallel transport along the closed curve gives you identity. So what we'll prove is the following. Take this curve. Okay, this is a curve in some n-dimensional space. Okay? Find the 2-dimensional surface whose boundary is this curve. Okay? If it has a curve in 2 dimensions, then there is a unique one, right? Just fill it. But imagine the curve in 3 dimensions, right? You can fill in many ways, right? You can just fill it by a plane, or you can just fill it by a basket, right? Something which hangs in 3-dimensional space. So in general, there is no unique space, right, which does this, but take any. Okay, take any 2-dimensional space which fills it. Okay. So what we'll prove is that if the Riemann tensor vanishes everywhere along the 2-dimensional space, then this matrix M is identity.
All such coverage
No,
or-
anyone. If you can find any 2-dimensional space on which the Riemann tensor vanishes, then this matrix is identity. On the surface, yes, on the surface. Is this clear?
This is true in any arbitrary dimension.
Yes, in any arbitrary dimension. So this is what will distinguish flat space from curved space, because if in curved space, the Riemann tensor, if I have a space with non-vanishing Riemann tensor, right, then there will be some closed curves on which this matrix is not identity. If it is locally vanishing. Yeah. So if it's locally vanishing, you can draw a small curve there in that region where this matrix is identity. Right? So if you have a space, some part of the space in which the Riemann tensor is vanishing, in that space, if you draw a curve like this, there will be no change under parallel transport. So this looks like a somewhat strange result, because this looks like a global result, right? C is big. Riemann tensor knows about the local points, right? So the way we are going to prove this is the following: that we take any surface, right, whose boundary is this, and then we'll think of the surface as being covered by a very fine net, right? Which means I'm just drawing in 2 dimensions. Okay, just take many small segments. And then we'll first prove that for each of these, this change is 0 to certain order. Each loop, each small loop. And then the big loop, well, it's not quite the sum. That you have to argue, right? That because big loop, this is a matrix, right? You are multiplying matrices. So you have to argue that you can multiply matrices appropriately. Okay? And nevertheless, you can prove that the big loop can be expressed as a product of these, right? And if each matrix in this product is identity, okay, then the result will be identity.
So small loops, if R is
0. Yes.
Will show that for the all loops it's identity.
It's identity, exactly.
And that will imply that if Riemann tensor vanishes everywhere inside the loop.
Yes.
Then
exactly. Because if it vanishes everywhere in the loop, then in every small loop, it's identity. Right? And so the big loop will be identity. Converse is no, converse is not true, because if you know a big loop, right, you cannot say there may be cancellations. But the point is, it may not be possible to choose coordinate system in which is identity everywhere, because if the Riemann tensor is non-zero in some region, right, in that region you can always draw a loop, right, so that no surface will have this property, right. So in that case, this matrix is not identity.
So what is the statement? Like, what implies what? If the space is curved, then there will exist some curve along which it's not identity.
Exactly. Okay, if the space is curved, I mean, that means if the Riemann tensor is non-zero in some region, right, there will exist some curve in the space where it's not identity.
that statement, the identity part is independent of coordinate.
Yes, indeed. So it's not a coordinate choice. Right? Now you are talking about the geometry in space, right? There are some spaces in which this may be 0, which are the analog of the flat space. Right? I mean, if it is identity for every closed curve, right? That is as close to flat space as you can get. Exactly. That's right. Exactly. Yeah. If all components of the Riemann tensor are 0 in one coordinate system, it will be 0 in all coordinate systems. Right? So this gives a geometric interpretation of what the Riemann tensor is doing. Right? In what sense it captures the curvature of space-time. Right? The non-vanishing Riemann tensor means that you cannot find a curve. Right? Not along that you can always find a curve along which parallel transport changes the vector.
Suppose I have something compact, like a sphere.
Yes.
If I draw a loop on a sphere, there will be two regions, right?
Yes.
Like, it doesn't matter what I consider inside the loop.
Yes.
Right. It may happen that here Riemann tensor vanishes, but on the other side it does not vanish. And something like
it may happen. If it vanishes in one region, you can use that to conclude that this matrix is identity. In the other region, there may be cancellations, right? That means in the other region, there must be cancellations, right? So you have to just find one region, right? One surface along which the Riemann tensor is 0 everywhere. Right? That is good enough. Yes, that can happen, right? So it's not the correspondence, right? Is not one-to-one in the sense that it can happen that a Riemann tensor is non-zero in various places, right? But this matrix is 1, right? And this is exactly the kind of thing that you are saying. That imagine that you have a space on that 2 ways to fill. In one way, it is Riemann tensor is 0 everywhere. In the other way, it is not 0 everywhere. Right? If there are more than 2 such regions, right? But as long as you can find one region where the Riemann tensor is 0, yeah, that's good enough to show that the matrix is identity. Because you can use that region to do this meshing, right? See, this matrix doesn't care about the region inside, right? This is just a property of the curve. This is an auxiliary construction, right? The fact that you are thinking of this as a collection of small loops. So as long as you can find one way to collect the small loops so that the Riemann tensor is 0 on every one of them, then this matrix must be identity.
Might not be possible to find such a surface where the Riemann tensor is all 0, right?
Yes. In general, it will not be possible. Exactly. Right?
Sort of somehow it's some special kind of geometry.
Exactly. So that's the reason why the Riemann tensor is non-trivial, right? That it gives it tells us that in the geometry it gives non-vanishing Riemann tensor means that in the geometry There must be some closed curves which will have this property, right? You can put the curve in the region where it is non-zero. Then obviously it's not impossible to find a surface on which Riemann tensor vanishes, right? Because at the boundary it doesn't vanish. So as long as the Riemann tensor is continuous, it will also not be non-zero inside the surface.
So we are here sort of interested in the contrapositive of this statement, which we are proving. Like if Riemann tensor vanishes everywhere, then this M matrix will be
Identity.
And if it is not identity, then there will be
somewhere the Riemann tensor must be non-zero. Exactly.
So that will sort of indicate that there is a curvature.
Exactly. Okay, so tomorrow there will be no class. We'll continue next week. Yeah, also there will be some more recent books, right? Son Carroll has.
So when we so where is the one that we is a body following that factor? Was it this volume?
Yeah, that's you got this volume, right? But you also put constraints on the state. Right? What kind of state you use to calculate for this? You use state invariant. So that basically is the statement that you should only use operators that invariant on. Yeah, otherwise you couldn't divide by the volume of the gauge. Right?
There's a part integral we use the gauge invariant.
Yeah, under the integrand is gauge invariant, right? Then you can factor it out. Right. So, but and once so you demand that the integrand is gauge, right? Only use operators.
So this means it's invariant under any gauge transform.
Exactly.
So we are in fact factoring out the not only the volume of the integral gauge transform, of the entire.
Well, the global is a very small part, right? Usual gauge transforms are the big part. Local gauge.
It's the one that vanishes at the
boundary. The one that doesn't vanish at the boundaries is one factor. So U1 is a UI alpha, right? The one that doesn't vanish at the boundary is trivial. That you can think of as global or local, doesn't matter. The ones that don't vanish at the boundary, but which vanish at the boundary. The one that doesn't vanish at the boundary is just one factor
at the boundary.
Yes. Right? The local ones are the ones by which you have to divide.
The local ones is just fixed. I mean, what I'm not understanding is how is this said smaller than the trivial gauge?
Local ones are infinite dimensional. No, every point will make a gauge.
Yes, but the global, there is a global transformation. It is the
finite dimensional.
Finite dimensional group, and now there are transformations which are local. Now they can either vanish at infinity or not vanish.
If that doesn't vanish at infinity, you just combine the global transformation and make it.
So it's like okay, it's a local transformation on top of a global.
Exactly. That's right.
Okay, I see.
The local transformation doesn't vanish at infinity, just combine with the global.
Just sufficient to look at the local transformation.
Exactly. So the independent ones, right? The one global and the one finite.
So you're saying this is true.
Or I'm just saying that if you take the original geodesic equation, right, and then get A as dxg, that satisfies by alpha. Dxu is the angle.
That's
Yeah, that's the thing. So now this, if the angle doesn't change, right, that means under parallel transport, the angle will be vector short. Because that gij and I n k, right? I mean, I could have written it as n I n. So if you have a geodesic between the two, right? A geodesic triangle vector goes over under parallel transport. This one goes over to this one. The angle shouldn't change. Angle here should be the same as angle.
tangent vector.
Tangent vector is parallelism. That already. The tangent to the geodesic here is the parallel transport of tangent vector.
So the tangent vector. So on this curve you have some tangent vector.
Yes. Those are just parallel transported.
So to themselves.
To themselves.
Okay.
So the tangent vector here is the parallel transport of tangent. Right? That is there. Now we are trying to get, see, this is the parallel transport of. Right? The angle is awesome. You do that. Right? So the parallel transport of that, then the inner product between the vectors here should be the same as the inner product. But this is only a case, right? It cannot tell you if, because there are many vectors which without that. To understand maybe what we are saying is, now, our dimension, angle is just one way.
So you're saying this is probably a two-dimensional.
It's probably two-dimensional, and that also parallel transfer analysis. What you want to define is parallel transfer as an arbitrary.
So, but for an arbitrary curve, you can't just say that you will pick the point you draw geodesic between them and transport and then draw.
Yeah, that you can. You put it infinitesimally close. Yeah.
But still, it's a 2D notion is what it is.
Yeah.
Okay, and point is that this parallel transport depends. So if you have a sphere. And if you take a vector on the north pole and you try parallelly transport along some longitude and then parallelly transport. So if you look at it on the sphere, if you do this parallel transport, use this definition that we have shown. Here it looks something like this, and here it looks something like that. That's some. But then now, if you look at parallel transporting this vector along this curve, but as an embedding in R3, then this vector will just go to it.
Yeah, because the point is when you go from the defined with R3 and the sphere, then every time you parallel transport, you have to project it back. Suppose you take a vector and tangent to the sphere, right? And parallel transport in R3.
Oh, I see.
It goes out of the plane of the sphere, right? That projection is what is watching this.
And that projection has to be done locally.
Exactly. At every point.
You can't just take the R3 vector and then finally